Second law of thermodynamics, on our way to becoming a thermodynamic energy specialist. The second law is a little bit tricky, and there's still people studying this law, so there's a lot to it. The actual law states establishes the concept of entropy as the physical properties of thermodynamic systems. So that doesn't really mean a lot to us. So what we can do is we're going to simplify this, and we're going to simplify it to my definition of it just for HVAC. And I like to word it as this. Heat moves from a warmer place or substance to a cooler, less heated place or substance. So it's moving from a warmer area to a cooler area. That's how heat's going to work. If they're both the same temperature, heat's not going to move. The bigger the temperature difference, the faster heat's going to move. We'll get into the speed of that shortly. I was taught that it's called simply heat seeks cold. We know that cold doesn't really exist, but if you want to think of it, heat seeks cold. Really, it's better to think of it as a cooler substance. That's how heat's going to move. Now, it goes much deeper than this. This is a simplified version to help you appreciate the second law of thermodynamics. So if I want heat to move, there needs to be a temperature difference. To give you an example with this, I have two pieces in the same room. I have this rag and I have this piece of metal. Which one do you think is cooler? Some of you may have said the rag, and some of you may have said the metal. But you're both wrong. The answer is really going to be they're both the same temperature. They've both been in the same height, in the same place, in the same room, at the same temperature. They're now equalized. The difference is my body temperature and the second law of thermodynamics. So my body temperature is around 98.7. These are both in the same room at 75 degrees Fahrenheit. My body temperature is warmer than both of these components. The difference is the heat moves from my body temperature through this material at a much slower rate. This conducts heat at a much slower rate. The metal conducts heat at a much faster rate. So when I touch the metal, heat's leaving my body and going to the metal at a much faster rate. So because the heat's leaving my body faster, I perceive this one as being colder. But in reality, the same temperature. If you were to hold both of these long enough, the heat would eventually replace itself. I would heat up this metal, I would heat up this component as well, and it would start to feel the same temperature. The smaller the metal, the faster your body is going to heat that up. So it's the heat movement. A lot of people talk about which is warmer, a carpet floor or a wood floor. And really the answer is kind of tricky. It's really they're both the same temperature. There is some changes in that depending on what type of heat's underneath, if there's air movement, blah, 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 what type of insulation. But let's think for the sake of argument, they're both identical in the identical type of soil. They're both a wood floor and there's a carpet floor exactly together. And you were to walk barefoot on one, which would feel warmer. And their carpet would feel warmer, but they're both the same temperature. Heat's going to leave my foot and go to that flat wood surface at a much faster rate than it would go into the carpet. Carpet is a type of insulator. It slows heat transfer. So when you're talking about the difference in the two, it's how you feel, not really the actual science behind it. A lot of people say they don't like tile floors because they're cold, but in reality, heat's leaving their foot, going to the floor at a faster rate, so the temperature of their foot drops faster. See the difference? This is how we have to think about heat. Warmer than, cooler than, heat transfer. So there's going to be three things that affect the speed of the second law of thermodynamics. These all tie in together, the movement of heat. So this rag is made of material that resists heat transfer. Most insulation types are built with a type of material that slows or resists heat transfer, such as fiberglass, foam, as well as dead air space, dead air pockets. They resist heat transfer. That's why we use them in the walls of houses. They help slow down the movement of heat. Other materials, most metals, also speed up or increase heat transfer. If I took both of these metals and put them outside in the sunshine during the hottest part of the day, they would both also end up being the same temperature. But as you touch the rag, it wouldn't feel as bad because the heat's leaving the rag into your body at a much slower rate. The heat leaving the metal would be at a much faster rate and it would be burning and I would have to set it down. So the material is a key. If I had one house built with fiberglass insulation and another house built straight with metal, the metal house would be much warmer because it's transferring heat from the outside to the inside at a much faster rate. So we use insulation to control heat transfer. But other times I want to increase heat transfer. And that's what we're going to talk about with different types of metals. Copper and aluminum work great for heat transfer. fast. So we use this evaporator coil inside of our house and also a condensing coil outside our house to transfer heat. So I'm going to run refrigerant through here, and I need the temperature of the refrigerant to be lower than the temperature of the air. Heat travels from a warmer substance to a lower substance. So if this is, say, 40 degrees and the air temperature is, say, 78 degrees, the air temperature is warmer than the refrigerant. So heat's going to leave the warmer air, travel to the metal, to the aluminum, from the aluminum to the copper, from the copper to the cooler refrigerant. But I want that to be fast. That's where different metals come in. If I built my evaporator coil out of a type of insulation, it would not be picking up that heat as well. So the material is very important. Sometimes I want a material with fast heat transfer. Sometimes I want a material that has much slower heat transfer. Very, very important. So the type of material plays a part in it. Another important part is the temperature difference. The bigger the temperature difference, the faster the heat's going to move. So if you're in the northern part of the hemisphere during the winter time, the outdoor temperature is going to be much, much lower than the house temperature. So the heat's going to be leaving the house going outside. As the outdoor air temperature drops, heat will leave inside the house to the outside the house at a much faster rate. If the outdoor temperature is just a little bit lower than the indoor temperature, heat's still going to travel, but a whole lot slower. So the material and also going to be the temperature difference. Let's think about the summertime. It gets very, very hot. It's like, think of the Midwest, for example. You're going to have an issue where you have it very, very hot outside, and it's going to be much cooler inside. So let's say the inside temperature is 78 degrees. The outside temperature is 100 degrees. Heat from outside is going to be coming in at a pretty fast rate. Big temperature difference. Heat's going to be moving through the insulation, heating up the air inside. This is where refrigeration comes in. We got to move it back to the outside. So if I want to get heat out of the air, I need my inside evaporator coil to be a lower temperature to get heat to leave the air and go to the cooler refrigerant. And outside, I'll have another set of coils, and I want to raise the temperature of that refrigerant so that heat leaves the refrigerant and goes to the cooler air outside. So if it's 100 degrees outside, I'll heat this up to, say, 120, 115 degrees. Now heat's leaving the refrigerant, going to the cooler air. We're going to get more into that shortly. So we know two things affect the speed of heat transfer: the material type, also the temperature difference, and the next one is surface area. So if you think about surface area, think about if you had a pie, and you had that pie, and you had two pies. Let's have two pies. Who didn't like two pies? You have two of your favorite pies, and you take one of them, and you cut it up into a whole bunch of little pieces, and you separate all those pieces. The other pie, you leave it out all together. Which one's going to cool off faster? And the answer is the one that's separated in little bitty pieces, because there's more surface area. There's more of the air touching more of that pie. On this side, the pie would be all in one solid piece, so there wouldn't be as much heat transfer. This also is very important with refrigeration. To get heat to move, we need material, surface area, and temperature difference. So the outside condensing coils nowadays are built a lot of times a lot larger than they used to be. I have more surface area. In other words, there's more of this metal touching the refrigerant, and there's also more of this metal touching the air. Larger surface area, there's also a temperature difference and the type of metal. So outside I'm rejecting heat, inside you're absorbing heat. A lot of our evaporator coils now, they make them in different shapes, but they want more surface area. More of that surface area helps speed up or assist in heat transfer. And a lot of times you can increase your surface area and reduce your temperature difference and have the same amount of heat moving. But we're going to be moving heat from a place that's unwanted to a place that makes little or no difference, or a place that we'd prefer it to be. Refrigeration, moving heat from a place that's unwanted to somewhere else. And that's all part of the second law of thermodynamics, how we get heat to move. Moving heat from a warmer place to a cooler place, temperature difference, surface area, material type. That affects the speed of the second law of thermodynamics.